The binomial theorem can be used for more than just expanding binomials of integer exponents. In fact, a while back in 1665, a pretty famous guy by the name of Isaac Newton showed that the binomial theorem is much broader than just multiplying these these binomials out. It turns out that you can still use the ideas of this theorem to evaluate numbers and expressions where the exponent isn't necessarily a whole number. In fact, he showed you could do it for any real number in a fairly complicated way. But we're going to look at an extension of this, restricting it to the exponent being a rational number or a fraction. So how can we do with what can we do with rational exponents? It turns out the formula itself, for a good reason, is very, very similar. There's a minor change to it, but we also need to grapple with how to deal with some formula, with binomial coefficients that have weird values of n. But I'm going to state it here that Newton showed this, that if you have some expression that looks like this, some binomial, that this is really an infinite series where we'll use R and n. This is really a series that goes as infinitely many terms of this form and of the same form as before. N choose R times a to the n minus R times b to the R. And this works for, and Newton showed this works for any exponent that's a rational number. And the symbol for that is boldface Q. Rational numbers being fractions with whole numbers in the numerator, whole numbers in the denominator. And this works for any, and also still applies for any value of R in the choose notation here, such that this is still going to be positive whole numbers. So positive integers. Okay. We should figure out how to calculate. This means that we can figure out how to do binomial coefficients where the n value is maybe a fraction or a decimal or even a negative number, but the bottom is a whole number, a positive whole number. So we need to know how in fact to calculate those things. And this is how you do it. It's the same. It's going to look almost identical to before, just to what we thought of with our factorial notation. Just to do n factorial, if n's not an integer, we're just going to do the following. We're going to take n and then multiply by n minus 1, then n minus 2, and we're going to keep going until we do r of these. So this is r values in a row, and then we're going to divide by r factorial. So if n is whole numbers, this does not change. If n is actually a whole positive integer, then this yields exactly the same formula, because we'll end up getting, eventually, if n's a whole number, one of these terms, and n is say smaller than r, like this is like 2 choose 4. Eventually, one of these numbers will be a 0, and everything will zero out. So this infinite term, and when r gets big enough, this infinite series ends up yielding a bunch of zeros at some point, if n is a positive integer, like the examples we had prior. So this formula still works for n is integers, like we saw, but also it's a little bit more broad, and lets us deal with like if n is like say 1/2, or like the square root of a plus b. This next thing I'm about to write down is not strictly necessary, but it's a pretty common way to write this formula that's going to be pretty useful for our calculations in a minute. So note that something we'll commonly see are expansions of this type: a plus b times x to the n. I'm just throwing an extra x in here. You don't strictly need the x, but the sorts of problems we're going to analyze tend to have them in them. That you can rewrite this expression as I can factor an a out of both terms. And I can rewrite this as, say, a times, and divide each of these terms by a. And that would leave a divided by a as 1. This divided by a is a fraction, bx over a. And all this is to the n power. And I do that because now I can peel out this value of a. Bx over a to the nth power. Reason I did this and rewriting it in this fashion is that now this binomial, one of the terms is in fact exactly 1, which means that in our term I can set either a or b. It doesn't really matter which one I choose. Maybe I'll choose a. I can set one of these to be 1, and 1 to every power is just 1 itself. So this makes the writing of the sigma notation a little bit easier, and it makes the writing of the individual terms a little bit easier by factoring out this a to the n power, which lets me rewrite this as a to the n times, and I'm going to write this using the sigma notation here. Sigma r equals 0 to infinity of now n choose r. The next term would be 1 to a bunch of powers, but 1 to any power is just itself, and 1 times something, it doesn't change. So I'm not even going to bother putting in the 1 to a power term. But then I'll also have a bx over a to the r. And this formula, this rewriting of the binomial theorem tends to help solve some of the problems we're going to see just a little bit cleaner and easier to use. Okay. So let's grapple with what some of this notation means, and then we'll attempt a couple of practice problems here. So first off, like how we calculate something like this, like half choose 4. According to our definition, half choose 4 is the following. It should be 1/2 times a half minus 1 times a half minus 2 times a half minus 3, and I'm going to continue going until I do r number of terms. And r is 4 in this case, so I have 1, 2, 3, 4 terms. So these are all the things that are going in the numerator. And the denominator is 4 factorial. So I can compute this. This is half times minus a half times minus 3 halves times minus 5 halves, all divided by 4 factorial. Let's see, this is 1 times minus 1 times minus 3 times minus 5, which is minus 15, over 2 times 2 times 2 times 2 times 4 factorial, which is 16 times 4 factorial. Or on my calculator, I can work that out real quick. How about a fraction minus 15 on top, and then 16 times 4, and the factorial button, if you didn't know, and Inspire at least, is you can either do by menu probability factorial, or there's an exclamation point next to the G here. Hit enter, and that tells me this is equal to negative 15, or negative reduces to minus 5 over 128, which is approximately negative 0.039063. Voila. Maybe it's a 3 sig figs be here. Note that your calculator, what's really nice is that your calculator does know how to do this as well. If you thought maybe I'll try using NCR, you'd be in business. So I can do 0.5, comma 4, and I get the same answer. So that's a good thing, and I'm going to use that from here on out to make my life a little bit easier. It also works with negatives, but maybe I'll write out by definition what this should be. It should be negative 2 times 1 less than negative 2, so negative 3, negative 4. I'm going to do 3 of those divided by 3 factorial. So this is negative 2 times 3 times 4 over 3 times 2 times 1. And this one actually works out pretty nicely. This is just negative 4. And I'll double check using my calculator just to make sure I didn't make any mistakes. I want negative 2, choose 3. Voila. Good deal. Okay, let's use this in combination with this generalized binomial theorem to get some expansions, some approximations for the series, and then we're going to use it to calculate some values. Actually, so maybe calculate some values that we couldn't, or it'd be kind of tough to do prior. Let's expand. We're going to expand this expression up until we get to the x to the third term. So let's see, first thing I notice is square root of 1 plus 2x, that's the same as 1 plus 2x to the 1/2. So this is an expansion where n is 1/2. And I want to get to the n to the x equals 3 terms. So I'll write out my expansion until I get, until r equals 3. I'm going to go r 0, 1, 2, and 3. So according to my recipe from above, how do I write these out? My recipe tells me to do this. I should do, my first term is going to be 1/2 choose 0 times a to the n minus 0, a to the third. In this case, a is 1. So that's good. 1 to every power is 1, so I'm going to omit it. And then 2x to the 0 power plus 1/2 to the first power, and then my second term 2x to the first power, because r and r should match, plus 0.5 choose 2 times 2x squared plus 0.5 to the third power times 2x cubed. And at this point, I'll get an x to the third term, and that's all I need for this problem. If you keep going, you'll get a more precise value, but problem only has to stop at x to the third power. So we can write this out. Anything choose 0 is 1. Anything times itself to the 0 power is 1. Anything choose 1 is itself times 2x. Half choose 2. Let's see, half choose 2 should be 1/2 times negative 1/2 over 2 times 2x, 2 squared x squared. Half choose 3 is 1/2 times minus 1/2 times minus 3/2 over 3 factorial times 2 cubed x cubed. Multiply this out, you get 1 plus half times 2 is 1x. If you multiply this term out, you get 0.5 times 0.5 on top. Divide that by 2. And then times 2 squared is 4. You get, what do you know, half, and it's negative because there's a negative sign. So plus negative 1/2 x squared. And lastly, the last coefficient should be 0.5 times negative 0.5 times negative 1.5 on top, 3 factorial on bottom, 3 times 2 times 1, and then I'm going to multiply that by 2 cubed, which is 8. What do you know? Another half. So my expansion of this is approximately this polynomial. I want to use this expression to approximate the value of 1/2. So if I want to approximate the value of the square root of 1/2, that means that I'm going to use this polynomial. That means a 1 plus 2 square root of 2x better be equal to square root of 0.5, or better yet, 1 plus 2x should be equal to 0.5. So if I find the value of x, From this, if I know what x is, then I can just plug x into my approximation, and I'll be able to approximate the square root of a half. So maybe solve for x. Divided by 2. That means that I need to plug in negative 0.25 into my polynomial expansion, and I'll have my approximation. So it's approximately 1 plus minus 1/2 times 0.25 squared plus 1/2 0.25 cubed negative, which is about 1 plus negative 0.25 minus 1/2 times negative 0.25 squared plus 1/2 times negative 0.25 to the third power, which is about 0.711 to 3 decimal places. Compare that to the square root, what your calculator would get if you just typed in a square root of 0.05. Not too bad. Pretty close. And if you kept adding more terms, you'd get a better approximation along the way. Which is a nifty trick, because this is clearly how these sorts of square roots are computed before calculators and programming was in effect. That this is how Isaac Newton or Leonard Euler or any mathematician up until the early 1900s would have been doing these sorts of calculations. It was the only way to, because we didn't have machines to do it. We'll wrap up with one more expression, or one more example. This time we're not going to bother with this approximation. We're just going to do similar to what we did in part A and calculate this term out to the x cubed term. Like this is the same as 2 plus x to the minus 1/2. Note the leading term is not 1. It would be this. The expansion is a lot cleaner to write if the leading term, if this value of a is 1. So I'm going to use this. I'm going to use this trick here to rewrite this polynomial so it is equal to so that one of the terms is 1. So I'm going to factor out this a to the nth power, which is to say this is 2 to the minus 1/2 power times 1 plus b divided by a. This helps me because now I can expand this guy to the x cubed term, and then in the end I just distribute a 2 to the minus 1/2 or a 1 over root 2 to everything. So this tells me this is 2 to the minus 1/2 times minus 1/2 choose 0 times x over 2 choose 0 plus negative 0.5 over choose 1 times x over 2 to the first power plus negative 0.5 choose 2 times x over 2 to the second power plus negative 0.5 choose 3 times x over 2 to the third power. You keep going, but our problem says we can stop at the third term. So let's work these out. We'll do this as fast as I can. 2 to the minus 1/2 times 1 times 1 minus 0.5 to the choose 1 is minus 1/2 times x over 2 minus 1/2 menu probability combinations minus 0.5 choose 2 is negative 0.125 or negative 1/8 times x squared over 4 plus Oh no, I mistyped. Darn it. That should be negative. I mean, this was not negative. This should be negative 0.5 choose 2 should be 0.375. Plus negative half choose 3, which is negative 0.3125 times x cubed over 8. And so on. And this answer would be fine, although it probably is best practice to multiply the coefficients with the denominators first. But in the end, this expression would be what you'd end up with. You could multiply out these together if you wanted. You wouldn't necessarily need to, as well as you could distribute this 1 over root 2. Again, you wouldn't need to, but it's something you could do if it makes it cosmetically look better.